Have you ever stared up at the night sky and wondered where it all came from? Not just the stars and the planets, but everything. All of space, all of time, all of us. What happened before the very beginning? This is perhaps the biggest question we can ever ask. To give you an idea of the scale we're talking about, the part of the universe we can see is about 93 billion light years wide. That distance is so vast that our minds can barely grasp it. Yet, all of that, every star, every galaxy, every grain of sand, started from a point smaller than a single atom. So, before we start our journey, take a moment to like the video and subscribe, but only if you enjoy exploring big questions and deep mysteries. We love to know who is on this journey with us, so please let us know in the comments where you're watching from and what time it is for you. Now, prepare your mind, open your curiosity, and join us on a journey to the edge of what we know. Let's begin our exploration together. Our story begins with an idea that has become the foundation of our understanding of the cosmos, the Big Bang. When we hear that name, we might picture a giant explosion, a firework in the dark emptiness of space. But that picture is a little misleading. The Big Bang wasn't an explosion that happened in space. It was the beginning of the expansion of space itself. Everything, everywhere, all at once, began to stretch. A good way to picture this is to imagine a loaf of raisin bread dough before it's baked. Let's say the raisins are galaxies. As the dough bakes and expands, every raisin moves away from every other raisin. From the point of view of any single raisin, all the other raisins seem to be rushing away from it. But there is no center to the expansion. It's the dough itself, the space between the raisins that is growing. This is what we see when we look out into the universe. In the 1920s, an astronomer named Edwin Hubble made a stunning discovery. He observed that distant galaxies are all moving away from us. And the farther away a galaxy is, the faster it's moving away. This is exactly what we would expect to see if the entire universe were expanding like that loaf of bread. If everything is moving apart now, it means that in the past, everything must have been much, much closer together. If we could rewind the story of the universe, we would see all the galaxies rushing back towards each other until everything in the cosmos was packed into an unbelievably hot, incredibly tiny point. The Big Bang Theory is the story of our universe, growing from that initial state into the vast, cool cosmos we see today. But how can we be sure this really happened? Besides the expanding galaxies, we have found a powerful piece of evidence, an echo from the very beginning of time. It's called the cosmic microwave background, or the CMB for short. Imagine the early universe. It was so hot and so dense that it was like being inside a star. It was filled with a blindingly bright, hot fog of particles and energy. Light couldn't travel very far without bumping into something. For about 380,000 years, the universe was stuck in this state. But as space continued to expand, it also cooled down. Eventually, it cooled enough for atoms to form, and suddenly, the fog cleared. The light that was trapped in the fog was finally set free to travel across the cosmos. Today, 13.8 billion years later, that very same light is still washing over everything. It fills every corner of the sky. We can't see it with our eyes because the expansion of space has stretched it out, turning it into very low-energy microwaves. But our special telescopes can see it. This ancient light is the oldest picture of the universe we will ever be able to take, and it carries with it a remarkable secret. The temperature of this light is almost perfectly the same everywhere we look, about 2.7 degrees above the coldest possible temperature, absolute zero. The amazing fact is that there are tiny, tiny differences in that temperature variations of less than 1 part in 100,000. These tiny spots, some a fraction of a degree warmer, some a fraction of a degree cooler, were the seeds. They were the spots where matter began to clump together, pulled by gravity, eventually forming the first stars, the first galaxies, and everything we see today. The Big Bang Theory is a spectacular success. It explains the expanding universe and the ancient light of the CMB, but it has a huge limit. It tells us what happened from the first tiny fraction of a second onward, but it doesn't tell us anything about the moment of the beginning itself. As we try to push our theories back to time zero, our mathematics gives us impossible answers, like infinite temperature and infinite density. This moment is what physicists call a singularity. It's not a place, but a point in time where our current understanding of the universe, our science itself, breaks down. It forms a wall, a barrier in time that we cannot see past. So, the great puzzle remains: what started the Big Bang? How can an entire universe appear from a single point? What, if anything, existed before that wall of time? This is the mystery we are setting out to explore. In our last step, we journeyed back 13.8 billion years and arrived at a wall. A moment in time, a singularity, where the universe was infinitely hot and dense. Our science, as we know it, cannot pass through this wall. But what happens as we get closer to it? What was the universe like in those first, crucial moments of its existence? To understand the problem, we need to continue our journey backward and watch the story of the cosmos unfold in reverse. Let's rewind the cosmic clock and travel toward that mysterious beginning. From our viewpoint today, the universe is a dark, cold, and mostly empty place. Giant clusters of galaxies are separated by immense voids of nothingness. Inside these galaxies, stars are born, they live, and they die. But if we start to rewind time, this familiar picture begins to change. Let's move backward by a few billion years. The universe is smaller, and galaxies are closer together. As we keep going, travelling back more than 10 billion years, we see the first large galaxies forming. They are chaotic, messy collections of stars, crashing into each other more frequently in the more crowded space. The universe is brighter and more energetic. Now, let's fast forward our reverse journey. We are going back to a time before any stars or galaxies existed at all. We are at about 380,000 years after the Big Bang. As we talked about before, this is the moment we see as the cosmic microwave background. Before this point, the universe was not transparent. It was a thick, glowing fog. Pushing our way back into this fog, we find ourselves in a place unlike anything we know. The entire universe is hotter than the surface of a star, and it is completely opaque. There is nowhere to hide from the heat and the light. It is everywhere. For hundreds of thousands of years, this is the state of everything. Let's keep rewinding. The clock now reads just 3 minutes after the beginning. The universe is now unbelievably hot and dense. We are in a cosmic furnace. The temperature is so high that atoms cannot hold together. Instead, we are in a sea of atomic building blocks, protons and neutrons. In these first few minutes, the entire universe was a nuclear reactor, forging the raw elements that would one day make up the stars. Almost all of the hydrogen and helium that exists in the universe today was created in this incredibly short period. It's an amazing thought. The stuff of the stars was made before the stars themselves even existed. Our journey is getting stranger. Let's push back to the first second of existence. The cosmic furnace is gone, replaced by something even more extreme. The universe is now a chaotic, churning soup of the most basic particles of matter and energy. Here, particles like electrons, quarks, and their antimatter opposites were being created from pure energy and then smashing into each other, turning back into energy. This happened at a furious, unimaginable rate. The universe was not just hot, it was a pure, violent sea of potential. The 4 fundamental forces of nature that govern everything today, gravity, electromagnetism, and the 2 nuclear forces were not separate as they are now. We believe that in this intense heat, they were merged into a single unified superforce. We are now very close to the wall. We are in the first fraction of a second. The further back we go, the hotter and denser everything gets. Finally, we arrive at the very edge of our understanding. The time is 10:43 seconds after the Big Bang. This isn't zero, but it's the smallest slice of time that our current physics can describe. This is known as the Planck time, and the era it defines is the Planck epoch. Here the energy is so enormous and the scale so small that our very ideas of space and time begin to lose their meaning. The smooth fabric of space-time that we know becomes a wild, bubbling quantum foam. Space and time are no longer a steady background. They are part of the chaotic energy of the moment. Here is an amazing fact to help us grasp the sheer intensity of this moment. Within the first second of its life, the universe's temperature was more than 10 trillion degrees. For comparison, the centre of our Sun, which we think of as incredibly hot, is only about 15 million degrees. The early universe was millions of times hotter than the core of a star. And this brings us to the great unknown. We still don't know how to describe the universe during this Planck epoch. Our two greatest theories of physics, which have been proven right time and time again, fail us here. One is Einstein's general relativity, which describes gravity and the universe on a very large scale. The other is quantum mechanics, which describes the strange rules of particles and energy on a very small scale. When we try to use them both to understand the Planck epoch, they give us conflicting, nonsensical answers. It's like trying to use a map of the world to find your way around a single room. How gravity works at this tiny quantum level is one of the deepest mysteries in all of science. Until we can unite these two theories into a single theory of quantum gravity, we cannot push our journey any further. We are at the wall, and the rules we used to get here no longer apply. We've journeyed back to the edge of time, to an era so small and so energetic our minds can hardly imagine it. We called it the Planck epoch, the first tiny tick of the cosmic clock. It is here that our journey backward hits a wall, and the reason is one of the biggest challenges in all of science. It's not that we don't have good theories about the universe. In fact, we have two of the most successful theories ever created. The problem is, at the very beginning of time, these two great ideas clash, and our understanding of physics breaks down. The first of these theories is Albert Einstein's general relativity. This is our master theory of the very big. It describes gravity, not as a force pulling us down, but as a curve in the fabric of space and time. A good way to picture this is to imagine a trampoline. If you place a heavy bowling ball in the centre, the fabric of the trampoline stretches and curves. If you then roll a small marble nearby, it won't travel in a straight line. It will follow the curve created by the bowling ball. Einstein realized that this is how gravity works. The Sun is like the bowling ball, and its immense mass creates a dip in space-time. The Earth, like the marble, is simply following that curve, which we experience as its orbit. This theory works perfectly for describing planets, stars, black holes, and the expansion of our entire universe. But when we rewind the universe back to the Big Bang, we are taking all the matter and energy of the cosmos, all the bowling balls, and squeezing them into a single, infinitely small point. General relativity tells us that this would create an infinitely deep curve in space-time, a point of infinite gravity and density. The math gives us an answer of infinity, which is just another way of saying the theory has broken. It cannot describe the singularity. Our second great theory is quantum mechanics. This is our master theory of the very small. If general relativity describes the graceful dance of planets and galaxies, quantum mechanics describes the strange fuzzy world of atoms and particles. In this world, things are not certain. A particle doesn't have a definite location until we measure it. Instead, it exists in a cloud of possibilities. Energy is not smooth and continuous. It comes in tiny, discrete packets called quanta. This theory is mind-bending, but it is also incredibly powerful. It is the foundation for our understanding of chemistry, electronics, and computers. Everything from your smartphone to a nuclear power plant works because of the principles of quantum mechanics. However, this theory has its own limitation. It was designed to work on a fixed stage. It assumes that space and time are a smooth, flat background on which the weird quantum dance takes place. It doesn't account for the fact that space-time can be curved and stretched, as general relativity tells us it is. For most of cosmic history, this isn't a problem. We can use general relativity for the big things and quantum mechanics for the small things. The theories can exist in their own separate worlds. But at the beginning of the universe, these two worlds collide. The entire universe was incredibly small, the domain of quantum mechanics. But it was also incredibly dense and full of energy, creating an immense gravitational field that requires general relativity. To understand this moment, we need a single theory that can handle both quantum effects and strong gravity. We need a theory of quantum gravity. When we try to imagine what such a theory might tell us, we get a strange picture. Quantum mechanics says that on the smallest scales, nothing is truly still. There's always a jittery, uncertain energy. If we apply that idea to space-time itself, it suggests that the smooth trampoline fabric of general relativity is, on a microscopic level, a bubbling, chaotic foam. So which is it? Is space-time smooth and elegant, or is it a wild, foamy sea? Our two best theories give us two different answers. We are trying to describe an entire ocean of energy, crammed into the space of a single water droplet, QM, and the rule books we have simply contradict each other. To grasp how strange the quantum world is, consider this amazing fact. According to the quantum uncertainty principle, even the vacuum of empty space is not truly empty. For incredibly brief moments, pairs of virtual particles, one matter, one antimatter, can pop into existence from nothing, exist for a fraction of a second, and then annihilate each other. Empty space is actually a fizzing, bubbling soup of these temporary particles. This tells us that the quantum world is a place of pure potential, where something can briefly emerge from nothing. The search for a unified theory of quantum gravity is the ultimate goal for many physicists today. How this deep conflict is resolved holds the key to understanding the singularity. Scientists are exploring several fascinating but unproven ideas. Perhaps our universe is made of tiny vibrating strings of energy, as string theory suggests. Or maybe space and time themselves are made of tiny indivisible chunks, an idea from loop quantum gravity. These are some of the paths that might lead us past the wall. Until we find the right path, we are stuck. We know what our universe is, but to find out why it is, we have to first figure out how to fix our broken physics. We have reached a barrier. At the very beginning of our universe, our two greatest theories of physics, general relativity and quantum mechanics, stop working together. They lead us to a point of infinite density, a singularity that our science cannot describe. This wall at the dawn of time seems to block our view of anything that might have come before. But what if the wall isn't real? What if our theories are simply pointing to a problem that doesn't exist? A new generation of ideas tries to solve this puzzle by getting rid of the singularity altogether. These theories suggest there was no single beginning, but perhaps an endless cycle. Let's explore one of the most captivating of these ideas, the Big Bounce. Imagine our universe is like a giant cosmic lung, breathing in and out over immense stretches of time. Or picture it as a bouncing ball. It starts expanding, the ball flies up, then the expansion slows and eventually reverses into a collapse. The ball falls back down. It compresses into a super-dense state. The ball hits the ground, and then it rebounds with incredible energy, starting a new phase of expansion, the bounce. In this picture, our Big Bang wasn't a unique creation event. It was just one bounce in a potentially infinite series of universes. This idea is incredibly powerful because it solves the singularity problem. In the Big Bounce model, the universe never actually reaches a point of zero size or infinite density. As the universe collapses in on itself in what we might call a big crunch, all the matter and energy gets squeezed into an unbelievably small volume. But just before everything crushes down to a single point, a new, powerful force takes over. This force, which might arise from the strange rules of quantum gravity we talked about earlier, would act like a cosmic spring. The more the universe is compressed, the harder this new force pushes back, until it overwhelms gravity and forces the universe to expand again. The big crunch turns into a big bounce, and a new universe is born from the ashes of the old one. If we were to witness this cycle, what would it look like? Let's imagine a universe before our own. It might have been filled with stars and galaxies, maybe even strange forms of life. For billions or even trillions of years, it expanded. But eventually, the outward push of expansion would have been overcome by the pull of gravity. The expansion would slow down, stop, and then reverse. Galaxies, once rushing apart, would begin rushing towards each other. Over countless ages, they would merge and collide. The night sky in this collapsing universe would grow brighter and brighter as everything got closer. Stars would be torn apart, their matter absorbed into a growing sea of hot gas. Eventually, everything's space, matter, energy would be compressed into a hot, dense fireball ready for the next bounce. Our universe, everything we see around us, could be the result of that bounce. This idea of a cyclical, eternal universe is not new. It's one of the oldest concepts in human history, appearing in ancient philosophies and religions around the world. The thought that there is no beginning and no end, only an endless rhythm of creation and destruction, has always fascinated us. Now, modern physics is giving us the tools to explore this ancient idea, not as a story, but as a scientific possibility. Here's an amazing fact that puts the scale of this idea into perspective. Some versions of the Big Bounce theory suggest that these cycles could be happening for eternity. This means that before our universe, there could have been trillions upon trillions of previous universes, each one collapsing and giving birth to the next. The 13.8 billion years that our universe has existed could be just a single second in a year of cosmic time. Of course, the biggest question is, what is the mechanism for the bounce? What is this mysterious force that can stop a collapsing universe and turn it around? This is still a major puzzle for scientists. Theories like loop quantum gravity, which suggest that space itself is made of tiny, indivisible loops, provide a possible answer. In that theory, you simply can't squeeze space down to a single point. There is a minimum possible size, but we don't yet have any proof that this is correct. The biggest challenge for the Big Bounce idea is to find evidence. Is it possible that our universe carries some kind of memory, a scar, or an echo from the universe that came before? The search for these echoes is what could turn this fascinating story into a tested scientific fact. We've just explored a mind-bending idea that our universe was born from the collapse of a previous one in a big bounce. This gets rid of the troublesome singularity and suggests our cosmos is part of an eternal cycle. But if this is true, is there any way we can know? Did the universe that existed before ours leave behind any clues? Is there a ghost in the machine of our cosmos, an echo of a time before time as we know it? The search for these echoes is one of the most exciting frontiers in science, a cosmic detective story of the highest order. So, where would we even begin to look for such a clue? Our best hope lies in studying the oldest light in the universe, the cosmic microwave background. Remember, this is the faint afterglow of the Big Bang, a baby picture of our universe when it was just 380,000 years old. This light is a snapshot of the moment the cosmos cooled enough to become transparent, and it carries with it a map of the tiny seeds that would eventually grow into all the galaxies we see today. If a previous universe left any kind of mark, a scar from the bounce, it would be imprinted on this ancient light. Our standard theories of the early universe, which don't include a bounce, make a very clear prediction about what this baby picture should look like. The tiny hot and cold spots on the map should be completely random. There should be no special patterns, no preferred directions, no strange features. It should look like a random spattering of paint, or the static on an old television set. For years this is what we thought we saw. But as our telescopes got better and our maps got more detailed, a few strange things started to appear. Scientists began noticing anomalies, features in the CMB that were not supposed to be there. Imagine you have a piece of paper with a beautiful random pattern drawn on it. Now, imagine you crumple that paper up into a tiny ball and then carefully try to flatten it out again. You might do a good job, but the paper will never be the same. It will always carry the creases and folds from when it was crumpled. Some scientists think the Big Bounce could be like this. The previous universe, as it collapsed, would have been crumpled by quantum forces. Even if it bounced back and smoothed out into our expanding universe, some of the creases from its former life might have survived, leaving a subtle imprint on the cosmic microwave background. When we look at our best maps of the CMB from satellites like Planck, we find a few of these potential creases. There's a feature nicknamed the cold spot, an unusually large and empty-looking patch of the sky that is colder than our theories predict it should be. There's also a strange alignment in the largest patterns on the map, sometimes called the axis of evil, because it mysteriously seems to line up with the plane of our own solar system. These anomalies are a huge puzzle. Are they the cosmic creases we are looking for the first real evidence of a universe before our own? This is where the detective work gets tricky. These anomalies could also be statistical flukes. It's like looking at clouds in the sky. Every now and then, you might see one that looks exactly like a face or an animal. It's highly unlikely, but given enough clouds, it's bound to happen eventually. The cold spot could just be a cosmic cloud that happens to look like something special. Scientists are in a heated debate, trying to figure out if these are just flukes or if they are pointing to a new, deeper physics. The fact that we can even have this debate is a testament to our technology. Here is an amazing fact. The Planck satellite that mapped the CMB was so incredibly sensitive that it could measure tiny differences in temperature across the sky, down to a few millionths of a degree. This is like standing on Earth and being able to measure the heat coming from a single rabbit sitting on the surface of the moon. It is this unbelievable precision that allows us to hunt for these tiny clues that might just rewrite the story of creation. For now, we are left with a tantalizing mystery. We have found some strange fingerprints at the scene of the crime, but we don't know who or what left them. We still don't know if these anomalies are the first whispers from a lost universe, or if our minds are just seeing faces in the clouds. To solve this case, we need more evidence, and perhaps a different kind of theory about how the universe began. The Big Bounce is one possibility, but there are others. What if our universe isn't part of a cycle, but something even stranger? We've been searching for echoes of a lost universe, sifting through the ancient light of the cosmos for clues that might point to a Big Bounce. But while the clues are tantalizing, they are far from certain. So now, let us turn to a completely different idea, one that has become a leading contender in the quest to understand the beginning. This idea also does away with a single, unique starting point, but not through an endless cycle of bounces. Instead, it suggests that our universe is just one small island in a vast, unending cosmic ocean. This story starts with a concept called cosmic inflation. It's a crucial add-on to our standard Big Bang theory. Scientists were puzzled by a few things about our universe. For one, it's incredibly flat. This means that on the largest scales, space follows the rules of simple geometry, which is a very specific and unlikely outcome. It's also surprisingly uniform in temperature, as we see in the cosmic microwave background. Why should two opposite sides of the universe, which have never been in contact, be the exact same temperature? To solve these puzzles, a powerful idea was proposed. In the very first fraction of a second after the Big Bang, the universe went through a period of astonishing hyperfast expansion. Here's an amazing fact to help us grasp the sheer violence of this event. During this inflationary period, which may have lasted for only a trillionth of a trillionth of a trillionth of a second, a patch of space smaller than a single proton could have swelled up to be larger than an entire galaxy. This expansion was faster than the speed of light. Now, this doesn't break Einstein's laws, because it wasn't an object moving through space, but the fabric of space itself that was stretching. This incredible stretching would have flattened the universe, just as stretching a crumpled piece of cloth irons out all its wrinkles. It would have also taken a tiny, uniform patch and blown it up to enormous size, explaining why our whole observable universe started out so consistent. But this powerful idea has an even stranger consequence. The physics that describes inflation suggests that once this process starts, it's very difficult to stop. It might stop in certain places, but it would continue raging on in others. This leads to the theory of eternal inflation. Imagine you have a pot of boiling water. The water itself is bubbling furiously and expanding everywhere. This is like the inflating ocean of space-time. But every now and then, a small bubble of calm, still water forms within the chaotic pot. According to this theory, our universe is one of those calm bubbles. Inside our bubble, inflation stopped. That moment, when the hyperexpansion ceased and its incredible energy was released to create all the matter and heat we know, is what we call our Big Bang. But outside our bubble, the cosmic ocean is still furiously boiling. The fabric of space-time is still expanding at that unimaginable rate, constantly creating more space. And in that ever-growing ocean, new bubbles are constantly forming. Each bubble would experience its own Big Bang and evolve into its own universe. Our beginning was not the beginning. It was just a local event, the end of inflation in our tiny corner of a much larger reality, which we can call the multiverse. This completely changes our question. We started by asking, what came before the Big Bang? The theory of eternal inflation answers, more inflation. The inflating cosmic ocean itself may not have had a beginning. It could be eternal, stretching infinitely into the past and producing bubble universes forever into the future. The question of before our universe becomes a question of outside our universe. We are no longer trying to look back past a wall in time, but trying to peek outside the walls of our own cosmic bubble into the vast churning foam beyond. This idea is breathtaking. But is it science? This is where we reach a huge problem. We still don't know for sure if eternal inflation is real. Because the space between these bubble universes is expanding faster than light, we could never travel to another bubble. We could never receive a signal from one. They are forever beyond our reach. So how could we ever prove this is true? The only faint hope is that in the distant past, another bubble might have collided with ours, leaving a unique circular bruise on our cosmic microwave background. Scientists have searched for such a pattern, but so far, nothing has been found. For now, the never-ending cosmic foam remains a beautiful, mathematically driven possibility, a potential answer to our ultimate question that might be forever beyond our ability to prove. We've just imagined a breathtaking reality, the eternal cosmic foam. In this picture, our universe is a single bubble in an infinite, ever-expanding ocean of space-time, a multiverse filled with countless other bubble universes. We accepted that we could likely never visit these other worlds, as they are expanding away from us faster than the speed of light. But that doesn't stop us from wondering. If we could peek into these other bubbles, what would we see? Would they be just like our own universe, filled with similar stars and galaxies? Or would we find something utterly alien, something beyond our wildest imagination? The answers that some physicists propose are stranger than any science fiction story. The key idea is that each time a new bubble universe forms, the fundamental laws of nature within it might be set differently. Think of it like a giant cosmic factory that produces universes. Each time a new universe rolls off the assembly line, a set of dials is spun at random. These dials control the basic settings of reality. One dial might control the strength of gravity, another might set the charge of an electron, a third could decide how many dimensions of space the universe has. In our universe, the dials were set in a very specific way, leading to the cosmos we know and love. But in another bubble, the settings could be completely different. Let's imagine we could visit one of these other universes. We step into a bubble where the dial for gravity was turned up much higher. Here, stars would be crushed under their own weight, burning their fuel in a flash and exploding as supernovae almost instantly. There wouldn't be enough time for planets to form, let alone for life to evolve. Now, let's hop to another bubble where gravity was set to be much weaker. In this universe, the initial clumps of matter would never have had enough pull to come together. Stars and galaxies would never form at all, leaving the universe as a cold, thin, and boring soup of gas for all eternity. What about the other dials? Let's enter a universe with just 2 dimensions of space instead of our 3. Here, everything would be flat. Life, if it could exist, would be like drawings on a piece of paper, unable to cross over one another without colliding. Complex structures like branes, with their vast networks of connections, would likely be impossible to build. Now, imagine a universe with 4 dimensions of space. We can't even picture what that would look like, but the laws of physics tell us that the orbits of planets around a star would be unstable. Solar systems would fly apart. Looking at these possibilities, we can't help but notice that our universe seems special. Its settings appear to be finely tuned to allow for complexity, for stars, planets, and us. Why? This is one of the biggest mysteries in science. The multiverse offers a startlingly simple answer. It's an idea called the anthropic principle. It states that we find ourselves in a universe with these life-friendly settings, for the simple reason that if the settings were any different, we wouldn't be here to wonder about it. It's a selection effect. It's like waking up on a planet and being shocked to find it has breathable air, but it's not a miracle. You are only having that thought because you are on one of the rare planets that does have breathable air. On all the others, you wouldn't be there to notice. Similarly, we live in one of the rare cosmic bubbles where the dials were set just right. The extent of this fine-tuning is astonishing. Here is an amazing fact. The expansion of our universe is currently accelerating, driven by a mysterious force called dark energy. The strength of this energy is measured by a number called the cosmological constant. If this number were just a tiny bit larger, its repulsive force would have been so strong that it would have ripped apart all matter before a single galaxy could form. Physicists have calculated that this constant is fine-tuned to 1 part in 10, 120. That's a 1 followed by 120 zeros. To suggest this is a lucky accident is, for many scientists, impossible to believe. But in a multiverse with an infinite number of bubbles, a universe with this exact setting is bound to happen eventually. This leaves us with a grand and perhaps unsettling vision of reality. A vast landscape of possible universes, most of them sterile and dead, but a few, like ours, with the magic combination of laws needed for life. But we still don't know if this picture is true. Is there really a landscape of possibilities? Or is there a deeper reason why the laws of physics must be the way they are? Is there a theory of everything that would show us that all the dials had to be set to these exact values? The search for such a theory is our next destination. We have journeyed into the strange world of the multiverse, a place where our universe is just one bubble among countless others, each with its own randomly set laws of physics. This idea of a cosmic lottery, called the anthropic principle, is one way to explain why our universe is so perfectly tuned for life. But it's a bit unsatisfying. It feels like we're giving up on finding a deeper reason. Is it possible that there is one single, master theory that explains why all the dials of nature are set exactly as they are? For decades, physicists have been chasing this dream, the dream of a theory of everything. The leading candidate for this ultimate theory is as elegant as it is strange: string theory. So, what is string theory? At its heart is a very simple and beautiful idea. It suggests that if we could zoom in on reality, down to a level far smaller than atoms, smaller than protons, smaller than anything we've ever seen, we would find that the fundamental building blocks of the universe are not tiny, point-like particles. Instead, they are unimaginably small, one-dimensional, vibrating loops of energy. They are like tiny cosmic guitar strings. This is where the magic happens. Just as a guitar string can be plucked to create many different musical notes, these fundamental strings can vibrate in many different ways. Each unique vibrational pattern, each note, corresponds to a different particle. According to this theory, a string vibrating in one way appears to us as an electron. A string vibrating in another way appears as a photon, the particle of light. Another vibration gives us a quark. Everything we see, all the matter, and all the forces that govern our universe, are nothing more than the different notes of a grand cosmic symphony being played on these tiny fundamental strings. For physicists, this idea is incredibly exciting because it seems to solve the biggest problem we've encountered on our journey: the clash between general relativity and quantum mechanics. It turns out that one of the many possible vibrations of a string has the exact properties of the graviton, the long sought-after quantum particle of gravity. String theory doesn't just make room for gravity, it requires gravity to exist. For the first time, we have a mathematical framework that naturally unites the world of the very big with the world of the very small. It has the potential to be the theory of quantum gravity we need to finally understand the beginning of the universe. And what does it say about the singularity? In string theory, the Big Bang singularity, that point of infinite density, disappears. Because strings are not points, they have a tiny, but real, length. They can't be squeezed into an infinitely small space. They can only be squeezed down to the size of a string. This smears out the singularity, replacing the wall of infinity with a finite, manageable, string-sized nugget. The laws of physics no longer break down. They can describe this state and, in principle, could even tell us what came before it. However, to make the mathematics work, string theory requires something extraordinary: more dimensions of space. The theory predicts that the universe doesn't just have the 3 dimensions we know, length, width and height, but 10 or even 11 dimensions in total. So where are these extra dimensions? The theory suggests they are curled up, or compactified, into a shape so tiny that we could never perceive them. A good way to picture this is to think of a garden hose. From far away, it looks like a one-dimensional line, but for a tiny ant walking on it, there is a second dimension, the tiny circle it can walk around. The extra dimensions of string theory are like that tiny circle, curled up at every single point in our universe. The scale of these ideas is almost beyond human comprehension. Here's an amazing fact. The strings themselves are thought to be on the scale of the Planck length, about 1,000,000,000,000,000,000,000,000th of a centimetre. To put that in perspective, if you were to magnify a single atom to be as large as our entire observable universe, one of these strings would be about the size of a tree. This is why we have never seen one. But here is the great puzzle of string theory. While it is a mathematical masterpiece, we have no experimental proof that it is correct. And it comes with a shocking twist. The theory that was supposed to give us one unique answer for why our universe is the way it is does the exact opposite. It turns out that there are a huge number of ways to curl up those extra dimensions, maybe 10, 500, different ways. Each way would result in a different bubble universe with its own unique laws of physics. So, our quest for the one true theory has led us right back to the multiverse. Is string theory a description of our one reality, or is it a blueprint for a near-infinite landscape of possible worlds? This remains one of the biggest unanswered questions in all of science. We've just seen how string theory, our leading candidate for a theory of everything, replaced the problem of the singularity with a new, equally profound puzzle: the landscape. Instead of one universe, it seems to predict a near-infinite number of them. This vision, born from the complex mathematics of curled-up extra dimensions, can feel a bit abstract. But what if those extra dimensions are more than just tiny, curled-up shapes? What if they are home to something vast? And what if an event within that higher dimensional space is the true source of our beginning? This leads us to one of the most dramatic and cinematic ideas for what came before the Big Bang: the collision of universes. This idea, called the ekpyrotic model, comes directly from the world of string theory. It asks us to imagine that our entire three-dimensional universe is just a membrane, or brane for short, existing within a larger, higher dimensional space. Think of it this way. Imagine a huge, dark, empty room. This room, with its extra dimensions, is what physicists call the bulk. Now, imagine that floating in the middle of this room are giant, perfectly flat sheets of paper, Each sheet is a universe, a brain. We are like tiny, two-dimensional drawings living on the surface of one of these sheets. Everything that makes up our world, our bodies, our planet, the stars, the galaxies is stuck to this brain. We can move around on the surface of our paper universe, but we can't jump off it into the empty room of the bulk. We are completely unaware that other sheets of paper might be floating nearby. The ekpyrotic model tells a story of what happens when two of these brain universes, floating parallel to each other in the bulk, slowly begin to drift together. Over countless eons, they get closer and closer, pulled together by a force that acts between them. Finally, they collide. The impact is not at a single point, but happens everywhere across the vast, infinite surfaces of the two brains at once. The energy released in this titanic, universe-spanning clap of thunder is almost beyond imagination. All of the kinetic energy from the collision is transformed into a fireball of matter and radiation, trapped on our brain. This moment, this cataclysmic clash of worlds, is what we experience as the Big Bang. What happens next is just as interesting. The two brains don't get stuck together. They pass through each other, or bounce, and begin to move apart again. As they separate, our universe, which is the hot matter and energy on our brain, expands and cools. The hot fireball thins out, allowing particles to form, then atoms, and eventually, the pull of gravity begins to gather this matter into the stars and galaxies we see today. But the story doesn't end there. The model suggests that the force that pulled the brains together in the first place is still there, like a cosmic spring connecting them. As they drift apart, the spring stretches, slowing them down until they eventually stop and begin to move toward each other once again, setting the stage for the next collision billions or trillions of years in the future. Our Big Bang was not the beginning, it was just the latest impact in an eternal, cyclical cosmic drama. The name ekpyrotic actually comes from an ancient Greek word meaning conflagration, or a great fire, perfectly capturing this idea of a universe born from a fiery collision. This model is a powerful alternative to cosmic inflation. It solves the same big puzzles, like why our universe is so flat and uniform, but in a different way. The brains are assumed to be very large and smooth to begin with, so when they collide, the energy is released evenly everywhere, creating a uniform universe from the start. And the brain model offers a beautiful explanation for another deep mystery. Here is an amazing fact. Of the four fundamental forces, gravity is shockingly weak. The electromagnetic force that holds a tiny magnet to your fridge can easily defeat the gravitational pull of the entire Earth. Why? In the brain model, all forces and particles are stuck to our brain, except one, gravity. The graviton, the particle that carries gravity, is special. It is not stuck to our sheet of paper. It is free to travel through the higher dimensional bulk. This means that gravity's strength is diluted because it is leaking out into the extra dimensions. We only feel a tiny fraction of its true power. So, how do we know if this is true? The ekpyrotic model is a direct competitor to the inflation model we discussed earlier, and they make different predictions. Specifically, inflation predicts that the early universe should have been filled with a storm of gravitational waves, ripples in space-time itself. The ekpyrotic model predicts a much quieter beginning with almost no primordial gravitational waves. We are now building experiments with the precision to search for these ancient waves. If we find them, it would be a huge victory for inflation. If we search and find nothing, it would give a major boost to the idea that our universe was born not from a single point, but from the epic collision of two worlds. On our journey so far, we have explored some of the most spectacular ideas in modern science. We've imagined a universe bouncing back from the collapse of a previous one. We've pictured our cosmos as a single bubble in an eternal, frothing multiverse. We've even witnessed a vision of our world being born from the fiery collision of two higher dimensional brains. All of these theories, in their own way, try to provide a physical story of what happened before our Big Bang. But now, we must pause and confront a question that is even deeper. a question that challenges the very words we are using. What if we have been asking the wrong question all along? What if the concept of before the Big Bang makes no sense at all? This leads us to an idea that is both elegantly simple and profoundly difficult to grasp, that time itself began at the Big Bang. If this is true, then asking what came before the Big Bang is a meaningless question. The famous scientist Stephen Hawking explained this with a wonderful analogy. Imagine you are an explorer standing exactly at the North Pole of the Earth. If someone were to ask you, which way is north? What would you say? You couldn't answer. From the North Pole, every direction is south. The concept of north ceases to exist at that point. It's a question that sounds sensible, but it is logically broken because the system of directions it relies on has a limit. In the same way, the Big Bang might be the North Pole of time. Our entire lives are built on the idea of a past, a present, and a future. We think of time as a line that stretches infinitely in both directions. But what if that's not true? What if the timeline of our universe has a starting point? If the Big Bang is that starting point, then there is no before for it to come from, just as there is no north of the North Pole. The Big Bang didn't happen at a moment in time. It was the moment that created time. This idea is a natural consequence of Einstein's theory of general relativity, which we've talked about before. Einstein showed us that space and time are not separate things. They are woven together into a single dynamic fabric called space-time. You cannot have one without the other. And as we've learned, the Big Bang was the beginning of space. Therefore, if space was born in the Big Bang, then time must have been born right along with it. The fabric of space-time itself came into existence at that moment. To understand this better, we need to think about why we experience time moving in one direction. Why do we remember the past but not the future? This is what physicists call the arrow of time, and it is deeply connected to a concept called entropy. Entropy is simply a measure of disorder or randomness. Think of an egg. An intact egg is a state of low entropy. It is very ordered and structured. If you drop it on the floor, it shatters into a disordered mess. Its entropy increases. You will never see the reverse happen. You will never see a splattered egg on the floor spontaneously gather itself back into a perfect, ordered shell. This is a fundamental law of the universe. In any closed system, entropy or disorder always increases. This relentless march from order to disorder is what gives time its forward direction. The Big Bang, the very beginning of our universe, was a state of incredibly low entropy. It was the most ordered state imaginable, with all the energy of the cosmos packed into a tiny, hot, uniform point. Ever since that moment, the universe has been expanding, cooling, and becoming more disordered. Stars burn fuel and radiate it away, galaxies drift apart, and complexity forms and decays. This entire 13.8 billion year story is the story of the universe, following the arrow of time, moving from that initial, perfect order towards a state of greater and greater disorder. Here's an amazing fact to tie this all together. The flow of time that you experience right now is a direct consequence of the low entropy state of the Big Bang. Every process that defines your life, from the metabolism in your cells to the memories forming in your brain, is part of this cosmic scale increase in entropy. We are all surfing the wave of increasing disorder that began at the dawn of time. If this is true, then the concept of before is erased. Time's arrow is defined by pointing away from the Big Bang. There is no arrow that can point to a time before that moment. But this leaves us with an enormous mystery, perhaps the biggest one of all. We still don't know why the universe began in such a perfect, highly ordered, low entropy state. It seems to be the most unlikely state imaginable. If we could understand the reason for this initial perfection, we might finally understand the true nature of time itself, and whether it truly had a beginning, or if our understanding is still missing a crucial piece of the puzzle. We have reached a profound conceptual wall. The idea that time itself began at the Big Bang seems to forbid us from even asking the question, what came before? Just as there is no direction north of the North Pole, there may be no time before the beginning of time. This feels like a philosophical dead end, a point where science must simply stop. But one of the greatest minds of our time, Stephen Hawking, refused to stop there. Along with his colleague James Hartle, he developed a theory that uses a strange and powerful mathematical tool to bypass this wall and offer a vision of a universe that has no beginning at all. This idea is called the no-boundary proposal, and to understand it, we have to talk about something called imaginary time. Now, this name is a bit confusing. It doesn't mean a made-up fantasy time. It's a real mathematical concept that physicists and engineers use all the time to solve difficult problems. It involves using imaginary numbers, which are based on the square root of -1. For our purposes, we can think of it as a clever mathematical trick. It's a tool that allows us to look at the universe from a different perspective, a perspective where the difficult problem of the beginning simply vanishes. Think of it like this. When we try to map the three-dimensional spherical Earth onto a flat, two-dimensional piece of paper, we run into problems. The areas near the poles get stretched and distorted, but the flat map is still a very useful tool for calculating distances. The switch from real time to imaginary time is a similar kind of mathematical transformation. It allows us to take the complicated equations of space-time near the Big Bang and turn them into something simpler and more elegant. When we do this, the dimension of time loses its special quality and behaves just like another dimension of space. In our normal view, using real time, the history of the universe looks like a cone. It starts at a single, infinitely sharp point, the Big Bang singularity, and expands outward. That sharp point is where our physics breaks down, but when Hawking applied the tool of imaginary time, the shape of the universe was transformed. The pointy problematic cone became a smooth, rounded shape, something like a badminton shuttlecock. This shape is finite, but it has no sharp point, no edge, and no boundary. It is completely self-contained. The best way to picture this is to once again think about the surface of the Earth. Our planet's surface is finite. You can't travel on it forever, but it has no boundary or edge that you can fall off of. There is no signpost on Earth that says, the beginning. The North Pole and the South Pole are not edges. They are just points on the surface that are geometrically the same as any other. According to the no-boundary proposal, the entire universe is like this. In imaginary time, the Big Bang is like the South Pole of the Earth. It's not a violent singularity where the laws of physics break, but a smooth, calm, geometric point that is part of the universe's overall shape. The proposal, then, is that the boundary condition of the universe is that it has no boundary. It doesn't need a creator or a cause to set it in motion, because it never had a beginning in the first place. It simply is a complete and self-contained space-time. From this timeless, four-dimensional space, our familiar universe emerges. As we move away from the South Pole, the geometry changes, and the mathematical dimension of imaginary time transitions back into the real, flowing time that we experience. The expansion of the universe and the arrow of time we talked about before appear naturally from this timeless, boundaryless state. This leads to a truly staggering possibility. Here's an amazing fact. The no-boundary proposal, combined with the laws of quantum mechanics, suggests that a complete, self-contained universe like this could pop into existence from literally nothing. Not from a vacuum of empty space, but from a state of no space, no time, and no matter. Quantum physics allows for spontaneous fluctuations, and Hawking's model suggests that one such fluctuation could have created everything we see. But like the other ideas we've explored, this one remains a profound puzzle. We still don't know if this vision is a true description of reality. Is imaginary time a real feature of the universe at its earliest moments, or is it just a beautiful mathematical story we tell ourselves to avoid the problem of infinity? Is the universe truly a timeless, self-contained object that created itself from nothing? It is perhaps the most elegant and complete answer to the ultimate question, but it remains an unproven and perhaps unprovable idea at the very edge of human knowledge. We have just explored one of the most profound ideas ever conceived, Stephen Hawking's vision of a self-contained universe with no boundary, no edge, and no true moment of creation. His theory suggested that the entire cosmos could have burst into existence through a quantum fluctuation from a state of absolute nothingness. No space, no time, no matter. This sounds like magic, a violation of the most basic rule we learn as children. You can't get something from nothing. And yet, this is not just a wild philosophical guess. The idea that something can come from nothing is deeply embedded in our most successful theory of reality, quantum mechanics. To understand this, we need to revisit the strange, jittery world of the very small. As we've discussed, the quantum vacuum of empty space is not empty at all. It is a bubbling, frothing sea of energy, which we called the quantum foam. Out of this foam, tiny pairs of virtual particles are constantly popping into existence, living for a fleeting moment, and then annihilating each other. This isn't just a theory. We have observed its effects. This constant flicker of existence tells us that on the smallest scales, the universe is always borrowing a little bit of something from the void of nothing. The rule that allows for this cosmic loan comes from one of the pillars of quantum mechanics, the Heisenberg uncertainty principle. In its most famous form, this principle says that you can't simultaneously know both the precise position and the precise momentum of a particle. But another version of the principle relates energy and time. It says that you can borrow a little bit of energy from the vacuum to create new particles, as long as you pay it back very, very quickly. It's like a cosmic bank. The universe allows for uncaused, spontaneous loans of energy, but the bigger the loan, the faster it must be repaid. A tiny loan can create a pair of virtual particles that last for an infinitesimal fraction of a second before they disappear, and the debt is cleared. So, if something from nothing is happening all the time on a microscopic scale, could it also happen on a cosmic one? Could an entire universe be the result of one of these quantum loans? The immediate problem is obvious. A universe is the biggest loan imaginable, and it has lasted for 13.8 billion years. How could such a massive debt go unpaid for so long? The answer might be one of the most beautiful ideas in all of physics. The total energy of the entire universe might be exactly zero. How is that possible? We are surrounded by energy. The light from our sun, the matter in our bodies, the radiation from distant stars. This is all a form of positive energy. But there is another kind of energy in the universe, the energy of gravity. Gravity is an attractive force. To pull two objects apart, you have to add energy to the system. This means that the gravitational field itself can be thought of as a form of negative energy. The idea of a zero-energy universe proposes that the positive energy of all the matter and radiation in the cosmos is perfectly cancelled out by the negative energy of the gravity that holds it all together. A simple way to think about this is to imagine digging a hole in flat ground. You end up with a pile of dirt, but you also have a hole. The pile of dirt is like the positive energy of matter. The hole is like the negative energy of gravity. If you were to take the dirt and put it back in the hole, you would be left with perfectly flat ground again. The total amount of stuff you created, dirt plus hole, is zero. The universe could be the ultimate example of this. All the stars and galaxies we see are the pile of dirt, and the vast gravitational field they create is the hole. Together, they add up to nothing. And if the total energy of the universe is zero, then according to the uncertainty principle, it could last for as long as it wants. The cosmic bank doesn't care how big your loan is, as long as the net amount is zero. A universe could, in principle, pop into existence from nothing, without any cause, and last forever, as long as its books are perfectly balanced. Here is an amazing fact that supports this idea. Our best measurements of the overall shape of the universe suggest that it is flat on the largest scales. According to Einstein's theories, a flat universe is one that contains a very specific amount of matter and energy. This amount, called the critical density, is exactly the amount needed for the positive energy of matter to be perfectly balanced by the negative energy of gravity. Our observations of the real universe are consistent with it having a total energy of zero. Of course, we are still far from proving this is true. We still don't know for certain if the balance is perfect. Measuring the total energy of the universe is incredibly hard, and there are still huge uncertainties. And even if the energy is zero, we still need a complete theory of quantum gravity to describe the specific mechanism by which a quantum fluctuation could create not just a few particles, but an entire universe's worth of space-time. The idea that the universe was created from nothing by its own laws remains a tantalizing and beautiful possibility. We have just ventured to the edge of creation, entertaining the idea that our entire universe with all its splendor might be a perfectly balanced equation of zero, a quantum fluctuation that emerged without a cause from a state of nothing. This is a powerful and unsettling thought, but it all hinges on that one simple-sounding word: nothing. In our daily lives, nothing means an absence of things. But when we are talking about the origin of the entire cosmos, what do we actually mean by nothing? As we look closer, we find that the void is not as simple as it seems. In physics, there are different levels, different kinds of nothing. Let's start with the most familiar kind of nothing, what we might call the classical nothing. This is the nothing of an empty box. If we take a container, pump all the air out, shield it from all light and radiation, and cool it down to absolute zero, we would have a perfect vacuum. We would have a volume of space that is completely empty of all matter and energy. For a long time, this was our scientific definition of nothing, an empty stage waiting for the actors to appear. But as we learned in the 20th century, this empty stage is not empty at all. This brings us to our second level, the quantum nothing. According to the strange rules of quantum mechanics, a perfect vacuum is impossible. The Heisenberg uncertainty principle guarantees that even in the most empty space imaginable, there are fields of energy that are constantly jittering and fluctuating. From these quantum jitters, as we've seen, pairs of virtual particles are constantly bubbling into existence and vanishing again. So, a physicist's vacuum, our best attempt at creating nothing, is actually a seething, energetic, and incredibly complex place. This quantum foam is the nothing from which a small quantum loan can be taken. But it's clearly a something. It is a physical reality with properties we can measure. So, to get to a deeper nothing, we have to go further. What if we get rid of the empty box itself? What if we get rid of space and time? This brings us to level 3, a nothing with no space and no time. This is the state from which thinkers like Stephen Hawking proposed a universe could spontaneously emerge. This is a much more profound emptiness. There are no places and no moments. There is no stage. It's hard for our minds to even grasp this. But even in this seemingly absolute void, a physicist would say there is still something left. The laws of physics, the rules themselves. Think of it like a powerful computer program designed to create a virtual world. Before you run the program, the world doesn't exist. There are no landscapes, no characters, no events. But the code, the set of rules and instructions that define how that world would behave if it did exist, is still there, stored on the hard drive. In this view, the laws of physics, the mathematical principles of quantum mechanics and relativity, are like that code. They must have existed, in some abstract, timeless sense, in order for the program of the universe to have been run. So, a universe from this kind of nothing is not really from nothing. It is a universe that arises from a pre-existing set of physical laws. This forces us to go to the final, deepest level, the absolute nothing. This is the nothing of philosophy. It is a state of total non-existence. No matter, no energy, no space, no time, and, most importantly, no pre-existing laws, no code, no potential for anything to exist. This is the truest sense of the word nothing. And from this state, it seems impossible that anything could ever happen. If there are no rules, what would cause a universe to begin? If there is no potential, what could it emerge from? Here, our science comes to a complete halt. The scientific method is the study of the laws of nature. It cannot, by its very definition, say anything about a state in which no laws of nature exist. And yet, the energy of the quantum nothing we discussed is not just a theory. Here is an amazing fact. Physicists believe that the energy inherent in the vacuum of empty space is the source of dark energy, the mysterious force causing the expansion of our universe to accelerate. The energy of nothing is the most dominant form of energy in our cosmos, and it is actively deciding our universe's ultimate fate. This leaves us with the ultimate unknown. Where do the laws of physics themselves come from? Are they eternal truths that exist independently of our universe? Or are they just random rules that happen to pop into existence with our cosmos? When we ask if the universe came from absolute nothing, we are really asking where its rulebook came from. This is a question that may lie forever beyond the reach of our experiments, pushing us to explore even more bizarre ideas about the fundamental nature of reality itself. Our quest to understand what came before the Big Bang has led us to a profound impasse. We've discovered that to ask about a universe from nothing, we first have to ask where the laws of physics themselves came from. This question seems to lie beyond the reach of science, a final, unanswerable mystery. When we hit a wall like this, it's often a sign that our basic assumptions about reality might be wrong. Perhaps we need to completely rethink our ideas about space, time, and information. Out of the deepest puzzles of black hole physics has come a concept so strange, so radical, that it sounds like science fiction. It's called the holographic principle, and it suggests that the universe we know might be nothing more than an illusion. The story of this idea begins with black holes. For a long time, black holes presented physicists with a huge paradox. According to quantum mechanics, information can never be destroyed. You can burn a book, but in principle, all the information that made up the book is still there in the form of smoke, ash, and heat. But what happens if you throw the book into a black hole? The black hole has a point of no return called the event horizon. Once the book crosses that boundary, it seems to be lost from our universe forever. Its information is gone. This created a major crisis in physics. In trying to solve this, scientists like Jacob Bekenstein and Stephen Hawking stumbled upon a clue that would change everything. They discovered that the amount of information a black hole can contain is not determined by its three-dimensional volume, but by the two-dimensional area of its event horizon. This was a shocking result. It's like finding out that the storage capacity of your computer's hard drive depends not on the size of the drive itself, but on the surface area of its outer casing. It makes no intuitive sense, but the math was undeniable. The information about everything that had ever fallen into the black hole seemed to be scrambled and stored on its 2D surface. This is where two other physicists, Gerard Hooft and Leonard Susskind, made an audacious leap of logic. They asked, what if this strange property isn't just true for black holes? What if it's true for any region of space? What if it's true for our entire universe? This is the holographic principle. It states that all of the information required to describe a three-dimensional reality, like our universe, can be completely encoded on a two-dimensional surface at its boundary. The name comes from a familiar technology, a hologram. A hologram is a flat 2D piece of film which, when illuminated by a laser, produces a fully three-dimensional image. You can walk around the image and see it from different angles, and it looks completely real. But the 3D object is an illusion, a projection. All of the information that creates it is stored on the 2D film. The holographic principle suggests that our universe is a hologram. We perceive ourselves as living in a rich 3D world, moving through space and time. But this reality, including us, could be a projection of information stored on a vast, distant 2D surface that surrounds our cosmos. The pixels of this cosmic screen would be unimaginably tiny, about the size of the Planck length, the smallest possible unit of space. This idea completely reframes our question about the beginning. If our universe is a projection, then the Big Bang might not have been the creation of a 3D space from a single point. It might have been the moment the projector was turned on. The true fundamental reality would be the 2D information surface and the physical laws that govern it. Our 3D universe, with its arrow of time and expanding space, would be an emergent property, a consequence of something much simpler happening in a lower dimension. The question, what was before the Big Bang, transforms into, what was the state of the 2D information surface before it began projecting our universe? Perhaps it was a timeless, static, and much simpler state of pure information. This may sound like wild speculation, but here is an amazing fact. This idea has found a solid footing in string theory. A famous discovery known as the S divided by CFT correspondence provided a precise mathematical dictionary that translates a theory of gravity in a 5-dimensional universe into a non-gravity quantum theory on its 4-dimensional boundary. It proved that, at least in certain theoretical models, a universe can be a hologram. A complex world with gravity can emerge from a simpler, lower-dimensional world without it. Of course, we are a long way from knowing if this principle applies to our actual universe. We still don't know what this boundary surface would be made of or where it would be. Is our experience of a third dimension truly an illusion? Is our entire reality just a fantastically complex movie being projected from the edge of the cosmos? The holographic principle is one of the most profound and mind-altering ideas in all of science, forcing us to question the very nature of the world we see around us. Section 15. We have journeyed to the furthest reaches of scientific imagination. We have stood at the edge of reality and peered into the possibility that our world is a hologram. We have considered a beginning born from the clash of universes, from an eternal foam of cosmic bubbles, and from a timeless, boundaryless geometry. Each of these ideas is a monumental attempt to answer the ultimate question, but presented side by side, they can seem like a confusing zoo of competing theories. Is science lost, with everyone just guessing in a different direction? Or is it possible that these seemingly separate paths are beginning to converge? Are these ideas truly in competition, or could they be different pieces of the same grander puzzle? Let's begin by looking at the role of string theory. We introduced it as a candidate theory of everything, an attempt to write the final, unified rulebook for the cosmos. We can think of it as a potential foundation upon which these other ideas can be built. For example, we talked about the ekpyrotic model, where our universe was created by the collision of two branes in a higher dimension. The very existence of branes and extra dimensions is a core prediction of string theory. So, the ekpyrotic model isn't a competitor to string theory. It's a specific story, a scenario that could play out within the string theory framework. What about the eternal inflation model, with its infinite ocean of bubble universes? This idea also connects beautifully with string theory. Remember that string theory predicts a vast landscape of perhaps 10, 500 different ways the universe's basic laws could be configured. The bubble universes in the eternal inflation model could be the physical manifestation of this landscape. Each time a new bubble forms, it could be born with one of the possible solutions from the string theory landscape, resulting in a unique set of physical laws. In this view, string theory provides the blueprints, and eternal inflation is the factory that builds all the possible models. Now, where does the big bounce fit in? At first, the idea of a single cyclically bouncing universe seems very different from an eternally inflating multiverse. But what if the two ideas are combined? Imagine the great cosmic foam, eternally bubbling and creating new universes. Perhaps the bubbles that form aren't all one-way trips. Maybe some of them, after expanding for trillions of years, have the right conditions to collapse back on themselves and bounce, starting their own internal cycle. Our universe could be one of these bouncing bubbles, living out its own cycle of birth and rebirth within a much larger, and still growing, multiverse. The two ideas may not be mutually exclusive at all. This brings us to the most abstract ideas we discussed: the timeless no-boundary universe and the zero-energy universe from nothing. These could be descriptions of how the bubbles themselves get started. The quantum fluctuation that allows a zero-energy universe to pop into existence could be the very mechanism that creates a new bubble in the inflating foam. Hawking's elegant, self-contained geometry could be the mathematical shape of a brand new universe at the moment of its birth, before its internal clock starts ticking. And what about the holographic principle, the strangest idea of all? This may be the most profound connection. The holographic principle isn't a story about what happened in time. It's a proposal about the fundamental nature of reality and information. It could be the underlying operating system on which all the other scenarios run. Whether our universe is a bubble, a bounce, or a brane collision, it might still be a holographic projection. The physics of the multiverse or the mechanics of a cosmic bounce could just be the 3D manifestation of a deeper, simpler set of rules playing out on a distant 2D surface. The hologram might not be a competing idea, but a deeper principle that governs all the others. The mathematical links between these fields are becoming stronger every year. Here is an amazing fact. The equations used to describe the chaotic surface of a black hole, which first inspired the holographic principle, have been shown to be mathematically equivalent to equations that describe the behavior of complex quantum fluids. This suggests that the universe is built with a deep mathematical unity, using the same elegant principles to describe vastly different physical systems, hinting that our search for a single, coherent story might not be in vain. We are, of course, still missing the final chapter that ties everything together. We don't yet know if this grand synthesis is correct. It is a beautiful tapestry of ideas woven together by physicists at the absolute frontier of our knowledge. Is there one master theory that will eventually unite all these threads into a single proven picture of reality? Or will one idea ultimately win out over all the others? For now, the quest continues, pushing us toward the future of this ancient question. We have woven together the threads of modern cosmology, creating a grand tapestry of ideas that speculates on the origin of everything. We've seen how theories of bouncing universes, an eternal multiverse, and holographic realities might not be competitors, but interconnected parts of a single breathtaking story. This grand synthesis is beautiful, but it is still just a story. Science is not just about telling the most compelling tale, it's about finding evidence to see which tale, if any, is true. So, after this long journey through the imagination, we must ask the most important question: how can we ever know? What new tools and new discoveries will help us turn these incredible ideas into proven facts? Our first and most powerful tool is one we have already met: the cosmic microwave background. This ancient light, this baby picture of the universe, is our most precious artifact from the beginning. Future telescopes are being designed to study this light with a precision we've never had before. They won't just be taking a sharper picture, they'll be looking for a very specific, almost invisible clue hidden within the light itself. They are looking for a faint, swirling pattern in the light's polarization, a property of light waves that describes their orientation. A specific kind of this pattern, known as a B mode, is considered the smoking gun of cosmic inflation. Finding it would be direct evidence of the gravitational waves that the hyperfast expansion of inflation would have stirred up. This is a crucial test. If we find these B modes, it would be a huge victory for the eternal inflation and bubble universe models. If, after decades of searching with ever more sensitive instruments, we find nothing, it will give a powerful boost to the competing ideas, like the ekpyrotic and big bounce models, which predict a much quieter beginning. Our second tool opens up a completely new way of seeing the cosmos. For all of human history, we have studied the universe by looking at light, but now we can listen to it. With instruments like LIGO, we have opened the era of gravitational wave astronomy, allowing us to hear the vibrations of space-time itself. Currently, we can only hear the loud shouts from recent cosmic events, like the collision of two black holes. But future missions, like the space-based LISA observatory, will be like a cosmic hearing aid of incredible sensitivity. Here is an amazing fact about this future technology. The LISA mission will involve 3 satellites flying in a perfect triangle, connected by laser beams over a distance of 2.5 million kilometers. These satellites will be able to detect a ripple in the fabric of space-time that is smaller than the width of a single atom. With this power, we might be able to detect the faint, ever-present hum of gravitational waves left over from the Big Bang itself. This gravitational echo could give us a direct window into the first trillionth of a second of the universe's existence, letting us see past the wall of light that blocks the CMB, and perhaps witness the true nature of the beginning. Our other tools are growing in power as well. New observatories will create vast three-dimensional maps of the universe, charting the precise locations of billions of galaxies. By studying the subtle patterns in this cosmic web, we can test our theories about the universe's initial conditions with unprecedented accuracy. And, of course, the search continues on the theoretical front. Thousands of physicists around the world are working to build a complete theory of quantum gravity, using the language of mathematics and powerful supercomputer simulations to explore what happens when space and time are pushed to their absolute limits. But we must also be humble. We still don't know if the answers we seek are within our reach. It is entirely possible that the era before the Big Bang left no observable imprint on our cosmos. The energy required to unlock these secrets might be forever beyond what we can create in our particle accelerators, and the signals from the beginning might be too faint for any instrument we can build to ever detect. The answer to the ultimate question might be lost forever, hidden behind a perfect, impenetrable wall, but the search itself is what defines us. The drive to understand where we came from is the noblest of all human endeavours, and it will continue to push our technology, our mathematics, and our imagination forward into the unknown. Word count: 1041. Our journey to the edge of time is coming to a close. We have stood at the wall of the Big Bang singularity, where our physics breaks and our understanding fails. We've peered over that wall at the breathtaking possibilities that might lie beyond. We have imagined a universe that bounces, part of an endless cycle of death and rebirth. We've pictured our cosmos as a single lucky bubble in an infinite and eternally inflating multiverse. We've entertained the notion that time itself is an illusion, that our beginning was a smooth, timeless point with no before, or that our entire three-dimensional reality is nothing but a complex hologram projected from a distant two-dimensional screen. We have found that all these ideas, from the colliding worlds of string theory to the quantum emergence of a universe from nothing, are becoming increasingly woven together into a single, grand, but still speculative, tapestry. The story of our origin is the greatest detective story of all, and the clues are faint and scattered across the entire cosmos. We are learning to read them in the ancient light of the cosmic microwave background, and to hear them in the faint gravitational hum of space-time itself. We have not found a final answer. We may never find one, but the quest has revealed a universe far stranger, more beautiful, and more mysterious than our ancestors could have ever dreamed. The search for our beginning is also a search for ourselves, for our place within this vast and silent cosmos. And so, we are left with one final lingering question. As we continue to build our tools and sharpen our minds, will we discover that the answer to what came before the beginning is written in the laws of physics, waiting to be solved like the final variable in an ultimate equation? Or is it a picture, an echo from a lost eternity, waiting patiently in the sky for us to finally build the eyes to see it?